In the last video, we learned what vectors were, that they're a quantity represented by magnitude and direction. We learned some basic geometric properties, how to add vectors, how to scale vectors, what a vector between 2 points, how we can express that. And now I want to take our knowledge of vectors a little bit farther and start explicitly expressing vectors in terms of their components. They're called components. So let's look at vectors in component form. Okay. So let's recall that we have, let's say we have just in the xy plane here, let's say we have a vector v with initial point at the origin, some vector v here. And let's say this has terminal point xy. Okay, so a vector v with initial point 0, 0 and terminal point xy is expressed in component form as v, and we use angle brackets. So the ordered pair xy with angle brackets represents the vector v, whereas our standard round parentheses represent the point. So this is the point xy, and with angle brackets, this is the vector xy. Okay, very different quantities. One is just a point, one is representing a vector that comes with direction and magnitude. Okay, and so in general here, and let me make a quick remark. Why do we express vectors in component form? Well, if you'll notice, component form is very helpful because it tells you how many units is your vector spanning in the x direction and how many units is it spanning in the y direction. You'll notice a vector creates a right triangle here, and the base of this triangle has distance x, and the height of the triangle has height y, right? And so it's helpful to express vectors in component form because we can think of this as how many units in the x direction is this vector spanning, how many units in the y direction is this vector spanning, right? And component form tells us exactly that, right? It tells us, okay, well, this vector is x units long, if you will, and y units tall, okay? And so this generalizes, right? This was a vector with an initial point at the origin. In general, let's say v is the vector starting at point P and ending at point Q, where P is the point, let's say, x1, y1, and Q is the point x2, y2. Well, then in component form, let's say then in component form, v is expressed as the difference of the x components, right? So x2 minus x1, and then in the y, it's y2 minus y1. So if we have, let's look here, let's say we have P, which is the point x1, y1, and we have some other point Q, which is the point x2, y2. Well, then the vector PQ is this vector here. This will be V, which we're writing as PQ, right? How you find the component form of this vector is x2 minus x1, y2 minus 1. x2 minus x1, you'll notice here if this is x1 along the x-axis, and this is x2, this distance down here in red between x1 and x2 is exactly x2 minus x1. And the distance between 2 points, say y1 and y2, this distance in blue is exactly y2 minus y1, right? And that gives us the height of the vector, whereas x2 minus x1 gives us like how long the vector is in the x direction. Okay, so let's do a quick example to make sure we understand how to actually express a vector in component form. So let's do an example here. Let's find the component form for a vector with initial point of -3, 4 and terminal point of 1, 2. Okay, so we can say V equals something, right? We'll write it over there. Let's look at a picture here. So we have -3, -4. So our initial point is in the third quadrant down here, right? This is the point -3, 4. Sorry, that's the point -3, -4. How about the point -3, 4? 1, 2, 3, 4. Up. So here's y. Here's x. Here we go. Let's call this point P. Let's call the initial point P and the terminal point Q. So this is our point P, which is -3, 4. And then the terminal point Q is 1, 2. So this is Q. And so geometrically, we understand that the vector V, starting at P and ending at Q, well, imagine that's a straight line, starting at P and ending at Q. Okay, this is our vector V. But what is this vector in component form, right? Well, in component form, we represent the x and y components of this vector by we take the final point minus the initial point. So take the terminal point minus the initial point component-wise. So what I mean is the x component for the terminal point is 1, and then we subtract that from the initial point, or the x component of the initial point, which is -3. And then we do the same thing for the y component. We take the terminal point's y component, which is 2, and we subtract the initial point's y component, which is 4. Right? And so we can simplify this to say that, well, this vector v is then the vector 1 plus 3 is 4, 2 minus 4 is -2. And so we can look at the component form and say, okay, well, this vector v, which is 4, -2, what does that mean? That means in the x direction, we march to the right 4 units. So 1, 2, 3, 4, which makes sense. In the y direction, we march down 2 units, right? Because -2. And so we can see we went 1, 2. We went down 2 units. Or sorry, let's start up here at this point, and we'd march down 2 units to this point. Right, so we can see this component form gives us a way of like algebraically representing what's happening geometrically. Okay, and so now that we've got an idea of how to represent a vector in component form, let's take a look at what that means for scalar multiplication and vector addition and subtraction and stuff. So let's look at scalar multiplication in component form. So scalar multiplication if we have v is the vector x1, y1, then kv is the vector kx1, ky1. And remember, for scalar multiplication, k is a real number. So we say k is an element of the reals. Remember this, epsilon means is an element of, and this script r means the real numbers. So this says k is an element of the reals. Right? So here is now how we represent a scaled vector in component form. Right here, you just scale each component, meaning you just take x1 and y1 are just numbers, k is just a number. So you take the product of k times x1 for the x component and the product of k times y1 for the y component. Now, what about vector addition? Okay, so we had v is x1, y1, and let's let w be x2, y2. Well, then v plus w has a very intuitive component form. If we take v plus w, we just add them up component-wise. So v plus w is then x1 plus x2 and y1 plus y2, right? Where now x1 and x2 are the x components of v and w, right? x1 and x2, you add them, and then you add the y components, y1 and y2, to get v1 plus vw. Excuse me, to get v plus w. And so that means vector subtraction has a very similar representation in component form. We can say v minus w, which we know is really just vector addition with v and negative w. That means that's just then x1 minus x2, y1 minus y2. Okay, and so now that we have a good idea for component form of a vector and how we can represent scaled vectors, the addition of vectors also, and the subtraction of vectors in component form, we can now come up with a formula for calculating the magnitude. Let's be able to now, we want to learn how to calculate the magnitude of a vector. Okay. And I don't know if I said this in the last video or not, but notation for the magnitude of a vector. So here's some notation. If v is a vector, we denote the magnitude of v by, we say, magnitude or norm the magnitude of v. Sometimes you'll hear me say the norm of v, which just means the magnitude or the length, right? So this is some notation for the magnitude of a vector. It's like a double absolute value sign here. This double absolute value sign of v, we just mean the magnitude of v. So let's come up with a formula for the magnitude of v now that we can express a vector in component form, right? So let's let v just be some xy, right? Where there's x represents whatever's in the x component, y represents whatever's in the y component. This doesn't even have to be a vector with initial point at the origin, right? This could be with an arbitrary initial point. I just want x to represent the x component and y to represent the y component. And now let's look at our vector v. So we have some vector v here. And what does this notation xy mean? It means the length in the x direction, right, or in the horizontal direction is x units. That's what the x component of a vector means. And what does this y mean, right? It means the height of this vector. Or if you were to project this vector onto the vertical axis, this length here is y. And this makes up a right triangle, right? And the magnitude of a vector should be the length of a vector. So the question is, what is the length of this vector? Or put more in notation that's more in alignment with our class right now is, what is the magnitude of v, right? That's what this question is asking. Well, we get a pretty easy answer thanks to Pythagoras. The length of this vector v here in black is going to be the magnitude of v. And Pythagoras tells us that the magnitude squared is the same as x squared plus y squared. And so we get a formula for the magnitude of a vector just based on the Pythagorean theorem, or which is also, in this case, a distance formula, right? Root x squared plus y squared. So you take the x component, you square it, you add that to the y component, which is squared, and then you take the square root of the whole thing, and this is a formula for the magnitude of a vector. So this is the magnitude. And now that we understand vectors in component form, we can understand a formula for computing their magnitude. And it's just given to us by the Pythagorean theorem. Okay. So there's a remark I want to make about magnitude here is what we can do is, so if you think about a force, right? Let's think if we were applying our understanding of vectors to a force, and we don't know per se the x and y components. Say we don't know this vector's orientation in space, but what we do know is its magnitude. We know how many newtons of force we're applying, say. So we can express components based on magnitude. So that's the note I want to make. We can express components of v via the magnitude. So again, for example, say it's a force and we only know how strong the force is. We don't know the x or y components of this force, or it's how it's behaving in space, right? And let's say we just have this vector v and we know its magnitude. Well, then I can tell you the x and the y components of this vector. The vector v is then comprised, if we have a right triangle here with interior angle theta, then we know that the horizontal or the adjacent side is going to be magnitude of v cosine theta, and the opposite side is going to be magnitude of v sine theta, just from our formulas of calculating sine and cosine. So that means the vector v, given the magnitude, is magnitude of v cosine theta, magnitude of v sine theta. And we can use this just from the magnitude. We can actually compute components. We can say, okay, well, I know the magnitude, therefore the x component is just the magnitude times cosine of this angle, right? And this angle is going to depend on the direction of your vector, right? Because a different vector is going to have a different direction, which just means a different theta value there. Okay. So next I would like to talk about unit vectors. So what is a unit vector? Unit vectors. Let's start with a definition here, just a definition of a unit vector. It's a special type of vector, one that we will be dealing with a lot, I would imagine. So a unit vector, we'll denote it as U for unit, is a vector in any direction with magnitude equal to 1. Hence unit, right? So a unit vector is any vector with a magnitude equal to 1. And these play a really important role in a lot of applications that we'll see throughout this section here. But so now if we want a unit vector in a given direction, right? So say we have a vector v in a given direction, but we want a vector in the same direction of v, but with magnitude 1. How do we find that, right? Say here, this has magnitude of v equals, or let's just consider v to have some magnitude greater than 1. Okay, so let's say that right now our only condition is that the magnitude of v is greater than 1. Then the unit vector in the same direction as v is given by the following formula. You simply take the vector v, but you divide it by its magnitude. This is a vector in the direction of v with magnitude 1. And this is important. This is a vector in the direction of v with magnitude 1. Okay. So let's look at an example. And I want to say that you don't even have to have this condition about the magnitude of v being greater than 1. I just wrote that so it would make sense that in the picture, my vector v is shrinking when it becomes vector u, right? If the magnitude of v is smaller than 1, then you're actually stretching your vector to get it to length 1. So I want to look at like an example here. If we have, let's say we have the vector v equals 3, 4. Okay, so we march wherever we start. We march over 1, 2, 3 units, and then up 1, 2, 3, 4, up to here, right? So here's our vector v. Okay, so I want to ask 2 questions. What's the magnitude of v? So that's the first question. The second question I want to ask is, what is, or let's find a unit vector in the direction of v. Okay, so let's handle the first one. What is the magnitude of v? Remember, a formula for the magnitude is that the magnitude of v is equal to square root of the sum of the components squared. Okay, and so for us, we just plug in, well, in this case, the x component is 3, so we have 3 squared. The y component is 4, so plus 4 squared, which is 9 plus 16, which is root 25, which is 5. So the magnitude of this vector, the length of this vector right here, is 5 units, right? And this makes sense because this is just then a 3, 4, 5 triangle, right? Now, 2, what's a unit vector in that direction, right? Well, based on the formula that we just learned, a unit vector in the same direction as another vector is simply 1 over the magnitude of that vector times that vector. So we're scaling this vector by 1 over its magnitude, okay? And this gives us, so that's 1/5, because we calculated that the magnitude was 5, times 3, 4, which then u is equal to 3/5, 4/5. And so we have that u is 3/5, 4/5. So what does that mean on the picture, right? On the picture, u is then much shorter, right? In fact, that's 1/5 the length of v. So this is u. And let's check that the magnitude of u is indeed 1. Let's check. Say on homework or on an exam or something, you think you found a unit vector in the direction of v, and you go to check the magnitude and it's not 1, that tells you that somewhere along the line the computation was incorrect, because otherwise, if the computation is correct, you'll always have a magnitude equal to 1. So let's take the magnitude of u. This is going to be the square root of 3/5 squared plus 4/5 squared. Well, 3/5 squared is going to be 9 over 25 because you square the top and the bottom. And then this is plus 16 over 25. And that looks like that's going to be root 25 over 25, which is root 1, which is indeed 1, which is good. That means the magnitude of this vector is in fact 1, which means our computation was correct and finding a unit vector in the same direction as the vector v. Now, there's 2 special types of, well, there's an arbitrary number of special types of vectors, which are called standard unit vectors. In 2 dimensions, there's 2. In 3 dimensions, there's 3. So let's talk about standard unit vectors. Okay. And in 2 dimensions, we have an x direction and we have a y direction. The 2 standard unit vectors, right? Unit meaning magnitude 1 is the vector 1, 0, which is the vector of length 1 along the x-axis. And we call this vector I hat. It's I with a little hat on it. So maybe that's not the best, interfering with the axis there. So this is the vector. The vector 1, 0 is the vector I hat equals 1, 0. This is one of 2 standard unit vectors in 2-dimensional space. The other one is 1 unit in the vertical direction, and we call this one j hat, which is 0, 1. Okay. These are the standard unit vectors in 2-dimensional space. In 3-dimensional space, we have 3. And so you can generalize this to n-dimensional space, right? In 3 dimensions, what do we have? Well, we have an x direction we have a y direction, and we have a z direction. So if you're not familiar with 3D, with graphing things in three-dimensional space, how you can picture this is that y and z, the y-axis and the z-axis are on your screen, and the x-axis is coming out of the screen towards you. That's how you can visualize what's going on here. And so in three-dimensional space, we still have I hat and j hat, right? But now I hat is the vector 1, 0, 0, and j hat is the vector 0, 1, 0, because it lies along the x and the y-axis. But now in three-dimensional space, we get a new one, denoted in blue, that's along the z-axis. And this is a unit vector, so meaning it has magnitude 1. And this is k hat, which is 0, 0, 1. And so you can see how standard unit vectors would generalize to n-dimensional space, right? It's just, you have one for every axis, and it's a vector along that axis of length 1. So we have I hat is in the x direction, j hat's in the y direction, k hat's in the z direction for three-dimensional space. And we can express any vector in terms of these standard unit vectors, which is why they're so important. So we can express vectors as what's called a linear combination of standard unit vectors. Okay, let's see how we can do this. Let's take a vector v, which is x, y. Let's do this in 3D because we want to gear up to handling stuff in a three-dimensional setting. This is applicable in 2 dimensions and 4 and 5 and etc. But let's express a vector as a linear combination of standard unit vectors, right? Well, the vector x, y, z is the same as the vector x, 0, 0 plus 0, y, 0 plus 0, 0, z, which is the same if we scale this as x times the vector 1, 0, 0 plus y times the vector 0, 1, 0 plus z times the vector 0, 0, 1. But 0, 0, 1 is just I hat. So this is x I hat, and you can see how this would extend now, plus y j hat plus z k hat. Okay, and so we can take any vector in component form and express it as a linear combination of standard unit vectors. And depending on the context, both have their advantages. Later, when we discuss cross product, we'll express vectors using standard unit vectors. And we'll get to that in a few lectures. But I want to introduce standard unit vectors now. So, we could do a quick little handful of examples here. If we had, let's look at like component form. Versus standard unit vector form, right? If we just had, well, let's see, we were looking at the vector, let's take like 3, -4, right? Well, in standard unit vector form, so like over here, we can say like v equals, right? In standard unit vector form, that's just 3i hat minus 4j hat, right? And so it's the same information, just encoded slightly differently. And again, we want to get comfortable with both representations of a vector, because in the future, certain representations are more advantageous than the other. So, if we were to have something like 15, 8, that could be like 15I hat plus 8J hat, or, maybe one more example, just so we can see here, would be like if we had the vector -2, 0, right? Well, there's no y component, which means it's 0 times j hat. So we would just represent that as like -2I hat, okay? So there's just a handful of examples of, it's not a tough transition between component form and standard unit vector form, but it's worth seeing some examples in the first place. So that's where I'd like to stop for this video. Next, what we're going to talk about is we're going to shift our focus to three-dimensional space. And we want to get comfortable with graphing equations in three-dimensional space. What do vectors look like in three-dimensional space? How can we visualize what's going on and extend some of the notions we've learned about vectors, about scalar multiplication, vector addition, vector subtraction, stuff like that. We want to extend that to the three-dimensional setting. And so that's where we'll go from here.